video is sponsored by Red Shot. The art of chemistry can truly be found within the structure of molecules. Determined by the number of atoms and electrons, a simple shape can turn to such a complex being.
Today we will be taking a look at the importance of molecular structure within organic chemical compounds.
And you might not come much into the contact with organic chemistry except during 1991's AP Chemistry FRQ questions.
However, its molecular structure and its bonds are what truly divides the line between organic and inorganic molecules. But before we talk about organic molecules, let us first review molecular structure.
Molecular structures are simply composed of two or more atoms bonded together to form molecules. These are different types of ways we can use to show our molecules, but we'll narrow it down to two most important types, Lewis dot structures and the VSEPR model. Lewis dot structures are 2D models that show the positions of the electrons and atoms, the bond and lone pairs, and even the charge. Do keep in mind, we only use it for covalent bonds and polyatomic ions, as the structure only shows the sharing of electrons. We construct it by firstly finding the positions of the atoms, categorized as the central and the terminal atom. Atoms that are generally more electronegative, or have tendency to attract more electrons, will be placed on the outer space as the terminal atom. While the first atom in the formula, or the one that has the least amount of appearances, are placed in the center of them. Hence the name suggests central atom.
Secondly, you will calculate the total amount of valence electrons of all atoms combined. If you are encountering a polyatomic ion, be sure to add or subtract valence electrons from the total count. It is recommended that you also calculate the number of bonds using the formula as shown.
Finally, go fill in those electrons on the atoms. Be sure to fill in 8 shared or lone electrons for the atom to achieve the octet structure, where the atoms are most stable. There are, however, exceptions to the octet rules, such as hydrogen, beryllium, boron, and many more. For polyatomic ions, you must also place a bracket and the corresponding charge.
From your newly constructed Lewis dot structure, you can see that there are certain electrons clumped together in 2 or 3 rows. Those are simply double or triple bonds, which tells us that there are increased bond strength and a shorter bond length between the atoms.
I'm finally done with this. What the?
Well, you see, there's also the existence of resonance structures, also known as isomers. These pesky little structures have atoms and bonds in different positions, yet are still considered as the same molecule. And another concept you seem to have missed is to check for formal charge.
Excuse me, what?
You use formal charge to find the most optimal and stable one among all the Lewis dot structures. It's also important to check resonance structures to make sure they are correct.
Meanwhile, the VSEPR model is an important component that shows a more realistic view by showing 3D shapes to grasp the full idea of what they actually look like.
Using Lewis dot structures in the valence shell electron pair repulsion theory, or the VSEPR theory for short, we can construct the preferred geometric shapes of such molecules. As the name suggests, valence electrons are arranged in a way to minimize the electron pair repulsion.
Along with the number of valence electrons and bonds, we can create the best possible shape, which introduces the 5 shapes of the category of what's known as the electrodomain geometry, consisting of linear, trigonoplanar, tetrahedral, trigonobipyramidal, and octahedral. They each have a different shape, angle, and number of atoms.
However, the VSEPR theory also states lone pairs and its effects on these molecules, creating greater repulsion forces on other electrons and usually ruining these ideal shapes.
And thanks to these lone pairs, we are introduced to a new set of shapes, aka the molecular geometry.
Ah, don't you just miss Lewis dot structures? Well, thankfully, organic chemistry tends to use easier structures for their molecules. Speaking of which, how can we apply all these concepts into the molecules of organic chemistry?
Well, based on the free. Dictionary, it states that the organic chemistry is a branch of chemistry concerned with the compounds of carbon.
Organic and inorganic compounds form the backbone of chemistry, with their primary difference being that organic compounds always contain carbon and inorganic compounds contain no carbon. The bonds within organic compounds are also almost entirely composed of carbon-hydrogen bonds, while inorganic compounds have a much rarer chance of these types of bonds existing.
Organic molecules are also unique in that they have well-organized and patterned general formulas. We are going to discuss the properties of hydrocarbons in order to gain a better understanding of the nature of organic compounds. Hold up. Let's first explain the famous structure used by almost all organic chemists, the skeletal structure. What makes this so iconic is its mere simplicity, with just a few steps. Let's say you have this molecular formula you simply don't have time to finish drawing before you have to turn your test in.
Instead of drawing every single carbon-hydrogen bond and getting an F, you could just leave diagonal lines on your paper, replace carbon atoms with vertices, and connect them together with lines. And as for hydrogen, abandon them. Leave behind the non-carbon hydrogen bonds and voila, your new structure.
Well, here's another example. Simply delete all hydrogens. 3, 2, 1. Go! And connect the dots. And done. For realism, make sure to show the types of bonds and its angles on zigzags. And let's get back to hydrocarbons.
Most of organic chemistry revolves around carbon molecules, specifically hydrocarbons. Hydrocarbons, as their name suggests, are molecules composed entirely of hydrogen and carbon. The simplest form of hydrocarbon comes in a linear form, for example methane, CH4, with more complicated forms taking up other shapes, such as a cycle.
As we focus primarily on the cycle of hydrocarbons, one may not ignore the categorization of this family of chemicals. Hydrocarbons are split into two groups, aliphatic and aromatic. Aliphatic hydrocarbons are hydrocarbons that are derived from lipids, and in itself is divided into three different groups: alkanes, alkenes, and alkynes. Alkanes contain a single bond, alkenes contain a double bond, while alkynes contain a triple bond. And due to their different bonds, alkanes are known as the saturated hydrocarbons, while alkenes and alkynes are known as unsaturated hydrocarbons.
Then we have aromatic hydrocarbons, which derive from the degradation of certain plant extracts. A special thing about the structure of these hydrocarbons is that they are much more stable than what their Lewis structures would suggest. They are grouped as an arene, which contains a benzene ring as part of its structure, or a non-benzenoid, which, despite their lack of a benzene structural support unit, contain a special stability.
Well, that's it for the video today.
Thank you for watching, and we hope you
You can create hydrants, skeletons, but can you obliterate enemies in rare